Just before the beginning of this video, please bear in mind that if I sound sleepy or tired, as one user has pointed out, bored, I think was the word, I'm not bored, I'm just actually recovering from a pretty bad stomach ailment, and so I'm just quite drained. Although doing these videos is something to keep me active and doing something. So in fact, I'm quite fine, and it's just the way I'm sounding right now. It's nothing to do with me being bored. In fact, I think this whole section is quite interesting, and I wish I could express myself better, but as it is, I'm not able to sound as chipper as my usual normal self. So please forgive the way I'm sounding right now. Alright, now on with the video. Hello again. Before going on, I want to point something out that's already different between what this program is, or what it says anyway about itself, as compared to if this were a C file. So what I've done is I've copied, oh, I didn't notice any difference, I've copied into this C file from our original test 1 the same code identically, except that in order to make this type, I have to use this type of declaration. Now, I don't know if you find this confusing. It's really quite simple, but the reason for this type of declaration, or the funny tag word, is Typedef. The way you use Typedef in general, if you say Typedef and then some thing that you want to make a type, and then the name of the type, in this case my rect. Okay, but that's the standard way. So for instance, I could omit this part, and now the type that I want to be called my rect would be a struct, something of type struct tag my rect. Oops. Now that's exactly this. That has exactly the same meaning. This should compile as well. So the way Typedef works is Typedef, the type that you want, and then the name that you want. Combining these together is take this word and taking that, put that here, then I've defined the struct in line, sort of, and then I've given this struct a type name. So all this is a Typedef definition where we're defining the struct at the same time as we're defining the type. That's all that means. Now, I want to show you that these functions are exactly the same. I'm toggling back and forth, trying to make it line up, sort of. Well, whatever. There's the move, expand, shrink, width, height, all the same. Okay? Now, here's our tests folder. with the 4 projects that are in there. If I go into test 1 and the debug, which is the intermediate directory for the partially built project, here you'll find main.obj. Now what I'm going to do is dump bin, and let's see, what was I here? Symbols. Okay, now I'm going to really see all that. Let's click into the clipboard. Okay, so here are all those functions we defined. Expand, shrink, width, height, top left, rect info. These are, I don't know why they're declared as externals. These are not really external. Width is not external. But that's just the way it writes it down. Okay, so this is what you would expect. Here's a list of the functions that the linker needs in order to link this program up and turn it into an executable file. Now, if I go over to CPP intro, and do the same thing, but it's not main anymore. This one, I'll put it in my clipboard. Now it looks like this. You get all these weirdo names for the functions. In fact, what it is these, what they call Mangles names, indicate to the linker the name of the function, but also the arguments it takes and what it returns and so on. Here the dump bin program has taken this mangled name and unmangled it for us and shown us what this translates to. So in fact, the name of the function, the arguments it takes, and so on, are included in the name. That is, the function and its parameters and even return value are included in its name. And what that allows you to do is have a function with the same visible name, but maybe taking different arguments. And so that function will have a different mangled name and will be unique and different. As an example, take this expand or shrink. I could make another expand function which takes a myrect pointer, but just one int to expand both x and y. Say like that. And to implement that, I could call the other expand. Well, you see it's showing that there are two functions with this name. this should compile as it does. And if I wanted to, I could do expand my rect by 30. Print out the info. And I'm going to put a breakpoint here just to prove to you that it goes to the right one. I want this to do a startup. So it's going here. Now it's calling another function called expand, which is not the same one. And run. And it would have had the desired effect. The width and height both changed by an amount that I specified, 30. Okay, so that's one new feature of C++ that we didn't have in C. We can have functions with the same name taking different different sets of arguments. So this function is in fact completely unique from the other expand. And the way the linker accomplishes that is through this name mangling. Each function, every CPP function, has an mangled name format, and that tells the linker all it needs to know about which function is which. Okay. Now, moving on to the paradigm shift bit. First, what I would like to do as a first example is, let's say, take this move. Now, in the C++ world, what we do is, instead of thinking of move as an operation which acts on rects passed in, we think of move as an operation of a rect. So that is, the declaration of this function goes in here. And since it operates on this rect, wherever it happens to be, it doesn't require any rect argument passed in. Now, how do we define the function? It's possible to write it down inside the struct declaration, but I'll put it outside and show you how that works. This now is a member, just as these variable things are members of this struct. And so the way to indicate that it is a member of this struct is to put the struct name followed by 2 colons here. Now, since there's no rect passed in, the way goes this. Okay? Now, somehow or other, when however this function is invoked, this left, right, top, and bottom, and so on, will refer to the members of the particular rect for which this is invoked. I'll leave just that one there, and get rid of all this. Now, in order to move this rect, we're not able to pass in a rect, so the syntax works this way. Just as you would reference a member like left, you'll notice move has become a member. So in fact, the syntax is like this. Now I would like to put beside this function one of the other ones so we can see the difference. Expand is good. Whatever. Now this may or may not compile. It compiles, that's good. Now I would like to examine the difference between how this works. For instance, how does the rect info get passed into this function as compared to the old C way. To do that, I'll just put a breakpoint here and look at the disassembly. Now for the expand function, pushing in reverse order, first 0, then 50, which is 32 hex. Then this EBP minus 14 is the address, would be the address where R is stored on the stack. R is a stack variable. Is pushed onto the stack. First loaded into here, pushed on the stack. Function is called, and then cleanup. Okay. In this case, for these arguments, A is 10 and 40 is 28. The arguments are pushed in their usual reverse order, but instead of pushing the EBP minus 14 on the stack, that's simply placed into the CX register and then the function is called. So we have a mixture of stack pushing, C call, or whatever, right to left pushing, and a register value, which is always CX. CX is always used for the address of the object being referenced. I'm going to step over this one. Now you'll also notice that there's no cleanup code following this call. The callee, the function being called, is in this particular instance responsible for the cleanup. So first push, put something into CX, that happens to be the same, what they call this pointer, and I'll call the function, which for some reason has that. Now, I think better to leave it like this for the moment. For some reason, it's allocating a storage area by pushing ECX, which happens to be this pointer, and it's now replacing that CX that it already pushed with itself, which has no real effect. But as far as the debugger is concerned, that's what is identified as this. This pointer points to the rectangle object, which this function, a lot of use of the word this, will be modifying. And since it's saved this ECX onto the stack, we can always retrieve it whenever it's required, when it needs to reference data relative to the rectangle object for which this particular call is modifying. This function can be called using any rectangle object, and so in those cases this value changes, this pointer changes. Now, we don't need to see the rest of the disassembly. Here is this. Left, top, right, and bottom. You can't see, but they have changed in this function call by these ones increased by 40. And I'm not printing anything out. So if I wanted to, I can print this out. What do I got going here? Expand and move. Does that make sense? Oh, 3 printouts. Okay, first thing was an expand, which did work. It expanded the width only by 50, and then the move by 40 in the x direction changed this to a 40, 10 in the y direction changed that. This also changed by 40 and this by 10. So this is the new way now of manipulating a rect object. The first thing that you'll notice, as I was talking about before, is parameter validation. We don't need to validate any parameters in here because we're not given a parameter. There's nothing to check to see if it's correct or not. It wouldn't be, well, R could be no, but that's not our problem. That's a problem of, just saying, I don't know how you would say no dot move. Okay. So now we can do a similar thing with all of these functions. Expand. Well, I'll fill them in. Pause this and fill them in. Okay, so I've taken some of those functions and moved them into my rect. These are now called member functions. Members of the struct or type my rect. Excuse me. Now, I've left out these ones on purpose because these are slightly different, being property style functions, and for those we got to deal with this const fit, which I'd like to explain separately. As it is though, this should compile, and it does, and it's working just as before. Okay, now, so now here's this may seem like a kind of a trivial change. All we've done essentially is moved a parameter from this side over to this side, and in truth that is almost exactly what we've done. If you remember, this pointer value was put on the stack ahead of these two. In fact, it's sort of behind. It's sort of where I've written my rect here in terms of the stack. It's at a BP minus area. It's sort of a local variable. But as you'll see, moving forward, there's quite a lot more to this little switch than initially meets the eye. Okay, Now, I wanted to say something else about this. What's going on? Right, yeah. Just a wording thing. Before we were thinking of the move operation as something we do to a rectangle. Okay. Now, after this switch, we think of move, something a rectangle does. That is not something that we're doing, but something the rectangle is doing. That's why we call them members. A rectangle can move, and so it has a function which is a member of its, as its data members are, and is a property of rectangles specifically. Rectangles move, and this is how it moves, by calling this function. And you cannot call this function with anything but a rectangle, this particular version anyway. Now, the next thing I want to tell you about before going on to those const ones is data hiding. There's another new keyword introduced in C++. Well, these aren't really keywords. This is a type of key word, the way we use these double colons. And that is this word private. Once I do this, these variables now are no longer accessible to the outside world. In fact, neither are these functions. What we would do normally is put the stuff we want people to use, the interface to this data, in the public area, and keep the private down here, let's say separate. Now we're going to see some problems. It won't compile, for one. We're going to get a lot of warnings. Cannot access bottom, etc., etc. The error is printf cannot access left, top, so on. And it's showing us, where the error is. The other thing is this setting of the variables through this initializer is no longer allowed. And in fact, R, the rectangle, is no longer considered to be just a plain old data type object. It's called non-aggregate, which cannot be initialized with initializer lists as I've got written here. So this would have to change, and will change, and we will change that momentarily. Okay, so what we'll do is first we'll just comment that away to get rid of that error. And we need to deal with these next. These ones that we're taking a const pointer to rect. Now, we define these sorts of functions in the same sort of way. Put it in here, put one of them in here. Now again, there's no rect passed in, so there's nothing here. Okay. Now this would seem to be correct, but where do we put the const? Remember, there's a hidden argument passed in. The rect is passed in, but it's not in the brackets. So we got it, but we still want to apply a const to it. And the syntax for that is that the const goes here, like this. So in our width function, this goes away, this goes here, const goes here, and there's no reference to that, and that's width. Okay? Same with the rest, I'll do in a minute. The other new keyword, which I'd like to switch to before continuing, is to do with this struct. In C++, generally the data parts are private, considered private, and we make public member functions. But we like the default. The default for anything that we start out with to be private, and there's a new keyword introduced for that, which is exactly like struct, 100% identical, called class, but in this case, the default is everything private, so I don't need this keyword for these. I can put them back where they were, but I can make these public. So there's public and private keywords, and when we use the word class instead of struct, the default is private, so all these are private, and in order to make something public, I have to say specifically, this is public, and the rest private. Okay, I'll fill in the rest quickly. Top left. Also constant. Bottom right. Now I have to declare these in the class as well. And now I'm starting to use the buzzwords class instead of struct, but it is the same thing. I'll try and collect all these. You can keep these in here if you want. It makes no difference, but it's better to get rid of them for clarity. And these are property type functions. They don't modify the rectangle. And that just leaves us with one more problem. I think we're okay. It's with these. Just this printf. Now, this here doesn't modify the rect. Why don't we just call this print_info, make it another constant number. Oops. Almost right. Now you'll notice that I can call width is a member, so I can just call it as is from in here. You can call a member function from within a member function without having to specify anything about which rect you're talking about. It has to be this rect. Okay. And now our program changes slightly. This is a file. And info. Oh, there we go. Well, of course, now we have an uninitialized. Now our problem is this bit. So that's the last remaining problem. How do we set the variables? One thing we can do is create functions that, like move and expand, do something. We could create a function to set the rect parameters, or we can invent something called a constructor. But for simplicity, let's just make a function set rect. Let's say. I'll change this eventually. And how did that go? Left, top, right, bottom. Okay. Now the implementation of this function is quite simple. I don't have to do these outside, but I'm going to stick with one way of doing things for now. And I'll show you other ways later. Now this presents a slight difficulty. Before this is what we would like. Okay, something like that. Now I don't have to present myself this difficulty. It's an interesting little puzzle here. Here I've named this variable passed in called left, which is the same as one of my member names. Now I could just call this something else. But to illustrate something new, if I want to specify in particular that the left I want to refer to is the left belonging to this rect, I can use the keyword this. Say that's equal to left. And that will take this left from the passed in argument list and set that equal to my left. But it's a little bit easier just to do this. And now I can just do it like that. Left, top. Compiling, run it, and there you go. Okay, so now we've switched to C++. Everything is the same, but now we're in C++ in a C++ environment where we are thinking of the rectangle as an object of its own that moves of its own, as it does. We don't move it; it moves itself by an amount we specify. It prints information about itself. If I had two rectangles, here's the same functions. Each one will have a different this pointer passed in and print info relevant only to itself. So the next example, I suppose, first I would like to change and get rid of this set so we don't have weird or uninitialized things. Well, I could leave this, but I would like to be able to do this setting at the same time as the declaration as we had before. And maybe we'll have another rect and see what we can do with that. Maybe we could see what the intersection of two rects is. Something like that. Okay. See you next time.